I know we're all really excited about our presentation today entitled, Can We Lower Our Biological Age? A rather provocative topic. And I'm even more excited about our special guest speaker today, Professor Andrea Maier. Professor Maier is the Unchu Seng Professor in Medicine, Healthy Aging, and Dementia Research. She's also the co-director at the Center for Healthy Longevity at the National University Health System at the National University of Singapore. She's also a professor of gerontology at the Vrije Universiteit in Amsterdam in the Netherlands. Professor Maier's research focuses on unraveling the mechanisms of aging and age-related diseases. She's leading international longitudinal cohort studies and geroscience interventions. During the last dozen years, she has published more than 370 peer-reviewed articles, achieving an age index of 68. So very prolific, and she's spearheading, she's had a number of contributions of her highly acclaimed, innovative, global, and multidisciplinary at-age research group. She's a member and advisor of several international academic and health policy committees, including the World Health Organization, evaluating the United Nations Decade of Healthy Aging. In 2022, she co-founded the first longevity medicine clinic in Singapore, the Chi Longevity, as Chief Medical Officer. She's the past president of the Australian and New Zealand Society for Sarcopenia and Frailty Research. She's the founding president of the Healthy Longevity Medicine Society, and she serves as selected member of the Royal Holland Society of Sciences and Humanities. We're very fortunate to have Professor Maier as a fellow of the Academy, and grateful to her for setting her alarm so early in the morning to be here today. I guess in some ways this is quid pro quo or payback for me having to get up so early today to present at her fantastic Healthy Longevity Medicine seminar series in Singapore. So Andrea, thank you so much for being here today, and we're all very much looking forward to your presentation.
Thank you so much, Professor Dudek. It was a pleasure hosting you a couple of hours ago, and it's a pleasure of being here, really talking about the new kid on the block in medicine. And I would say that is longevity medicine, or even rather healthy longevity medicine. And you gave me the very provocative title, Can We Lower Our Biological Age? And I must say, absolutely, yes, we can, and we should. And because we already can it, and hopefully at the end of the presentation, you will not only be convinced, but you have the tools to maybe also open that and that new area of research and clinical care at your center with your patients. Some of you may find this photograph quite provocative. I like it because it is really depicting the beauty of our body. And what this photograph is also depicting is that sometimes we are just looking away. Despite of the beauty, we are aging at this moment in time. Everybody here in the room is aging consistently. And it is very likely that we are not maintaining our body in the shape as we had the second before, because we are deteriorating, because we are accumulating damage, and therewith we are declining in function, not only cognitively, but also physically. And in the end, our body has a very nice mirror of what's happening in the inside, and that is the outer side. And very often, especially in the field of aesthetics, we are focusing on how we look like, which is very important. It also gives a very nice insight of our character sometimes. But most importantly is that the beautiful organ skin is giving us a really nice insight of what's going on, how much accumulation of damage we already have. So we are talking about aging today. We're talking about what chronological age is and what biological age is, and especially how we can lower the biological age. So I will talk about the new field, diagnostics, and then go into interventions, and then zoom out a little bit what we could do globally together. first of all, and everybody will know that, is the population on Earth is aging. And I like this slide because this slide is not only giving the population aged 60 years or over or 80 years or over, but it also stratifies it per continent. And I am, as a German passport holder living in Asia, we were asked by the government as a group of researchers to really not only analyze how the population is changing, but also how we could add health to an aging population, not only in Asia and in Singapore, of course, but worldwide. You see that there's an exponential growth of the population aged 60 years and over in the coming 2 to 3 decades. And this is absolutely not a problem, but this is, I think, a challenge. And what it also is really the end result of our not only beautiful sanitation technique that we all have running water now, but we also are having lots of medical systems which keep us alive, sometimes in a non-healthy way. So I think this is just the end result of a beautiful hospital system, of an outpatient system, of medical innovations we have around the world. Next to, coupled with, in some countries, a very low fertility rate. I can just speak for Singapore at this moment in time. Our life expectancy is very high. We are one of the countries with the highest life expectancy. It's 85.5. We always think, okay, are we the longest living nation, or is it Switzerland, or is it Japan? It doesn't really matter, but the life expectancy is high. And on the other side, we have a fertility rate of 0.7 at this moment in time, which means that in a couple of decades, we have lots of individuals who are much, much older and might have lots of age-related diseases. And with chronological age, the diseases come. And roughly, as also a geriatrician by training, you can remember that at the age of 80% of the population has at least 2 or more chronic diseases. At the age of 70, it's 70%. At the age of 60, it's 60%. So with chronological age, there is lots of medical needs for us in the conventional healthcare system. And that goes along with lots of costs, of course. I just depict on the left-hand side how many costs we have for different individuals at certain age groups. If you look at individuals being age 65 and older, the ones with no chronic disease in Singapore have a cost of nearly 3,000 Singapore dollar. And these are data from 2018, which is roughly 2,200 US dollar. On the other hand side, if somebody at the age of 65 and older already accumulates one chronic disease, it is nearly already 6,000 Singapore dollar, and it is much, much higher at the age of 15,000. Is that only in Singapore? No, of course not. It's around the world. We are spending lots of healthcare costs and GDP in the end on health, especially for older individuals. And only it depends on the country you are living. A very, very tiny percentage is being spent on prevention. Okay, so we know we are getting older, we have lots of diseases. If we could slow down the aging process, and therewith, because the aging process is the pathophysiological mechanism behind the accumulation of aging diseases, and we would be able to slow it down, how much in terms of dollars would that be worthwhile? And here I depict very nice work of Andrew Scott from the London Business School, but also David Sinclair from the US, you might know him. They calculated if we would slow down the aging process and increase, not health span, which is the year without age-related diseases, but the lifespan just by 1 year, in the US, that would be worthwhile 38 trillion US dollar. So that's a huge amount. So why is that? If we just increase the lifespan, because most of the times you also increase productivity. You increase, sometimes if you enable health, you have less absenteeism. People might want to, and also might be able to work much, much longer. But most importantly is also, if we would tackle aging and we would prevent in age-related diseases, that also then the cost, the high costs for all the age-related diseases would be much, much lower. So having cost, having a possible value proposition, because in the end, I will show you that we can diagnose the biological age and we can also intervene with it. We need an enabler. So we need to have something in hands that as a physician, we can say, yes, I'm diagnosing you now to be a fast ager or a slower ager, and we would like to prescribe interventions. So roughly 20 years ago, we started, it was not me at that moment in time, but the entire field was starting to talk to the WHO, the World Health Organization, to get an ICD at that moment, not an 11 code we have at the moment, but an international classification of disease code to enable to diagnose aging associated symptoms, conditions, etc. And in the end, aging as a mechanism itself, that we can actually bring in diagnostics, in interventions into clinical care. And I can tell you there is lots of debate about the code CT90 at this moment in time, and we have another code, who to use it, where to use it, and why to use it, how frequently to use it, and if to use it at all. This discussion is being led by prominent researchers, and including the Health Longevity Medicine Society, but also including other societies, for example, the Geriatric Society, because the Geriatric Society is still arguing to have a code for frailty, for example. And as the definition of frailty is still a little bit unclear, some of you might not agree with it, some might. There is lots of discussions if we can come up with a different terminology with the WHO to really advance both fields, the preventative part, so the healthy longevity medicine, and the geriatric part. But in the end, if we would succeed, there would be, and we call it a longevity dividend, there would be a huge opportunity to not only gain health, but also to gain economic growth by slowing down the aging process and therewith preventing age-related diseases. And you might already think, okay, if aging is the origin of age-related diseases, and we have so many and it's so costly, and you also reflect maybe on your own aging trajectory, I'm reflecting very often. I think I am aging, definitely. If I look at photographs of myself a decade ago and 2 decades ago, I really changed, not only from the outer side, but also from the inner side and my physical function and my capacity of all my organs. So knowing that, you also know that 100% of the population is aging. And that led to an explosion in the last decade of a new ecosystem. And that's not only the wellness ecosystem, but it's the longevity ecosystem. So here you see a slide being not readable, except of that nearly every country in the Western world is focusing at the moment on the longevity ecosystem. It's on not only that companies are investing in it, and also multinationals, but also we have lots of investors and we have lots of government agencies who now see, okay, we know what the projections are, let's do something, and also see it from an economical possible gain to make the best out of it for society. So we have more than 50,000 a company, and it's growing exponentially. We have a huge amount of investors and lots of R&D centers. And you see your own country, the US, is absolutely at the forefront. And but Singapore also plays a tiny role. So I would like to conceptualize a little bit what's going on during the aging process in the next slide. And this is really knowledge everybody should know already in basic school. And I think you absolutely know it, but please allow me to show you the slide, because I really want to make a point, and that we should not dichotomize health as we normally do in clinical practice. I'm an internal medicine specialist and geriatrician, and most of the times my patients come to me and say, doctor, do you have good news and bad news? Which means that we are dichotomizing what we are doing. And that's great, because it really helped us in the last 50 years to understand what is normal and what is abnormal. But it's a very, very rough indication of how the body is functioning. Of course, if we look at organ functions and organ performance, you can have the brain, the heart, the lung, it doesn't matter where you look like. From the age of 20, 25, it's very likely that you see deterioration, steep deterioration during the aging process of an individuals, and that's depicted here. What do we do in clinical practice? We have guidelines, and it's very good that we have guidelines, and they should be of higher standards, but we say at a cutoff point, we call it a disease, we have an ICD-11 code, we therewith not only diagnose it, but we treat it. So we are diagnosing a state which is quite a static state at that moment in time, and say, now you are diabetic and now you have hypertension. What we try to achieve in many of the countries, and I grew up medically in the healthcare system in Europe, we are trying to bring, especially in the GP services and the primary defense line of our ecosystem, we bring in prevention. And what do we mean? Very often, we say we want to delay the onset of diabetes, of hypertension, of that individual who is already a pre-diabetic, of has a little bit of a higher blood pressure. And we do lots of interventions. Very often we say, okay, you should eat less, control your weight, and move more. And we try therewith to prevent that onset of that disease. So really turning the needle a little bit more to the right and saying, oh, the onset is delayed by 1 or maybe two years, or at least a couple of months. And we often do that at ages where it might be already too late, because the aging process already starts much earlier. It is very good. It's not a criticism that we are doing it, because this is the first step of really on population level to increase and optimize health of individuals. But it is not, and there really healthy longevity medicine kicks in. It's not that we should wait until we are a pre-disease individual, but we should all ask our patients, and even if they're not patients because they don't have any diseases and they are not diagnosed yet and they are only aging, can we optimize your body at this moment in time? So normal is not enough. What we normally do in clinical practice, we get our lab results back and everything is in the black zone, and we say, good. But can we even optimize it to a level which means and optimize that we are avoiding and lower the risk of the incidence of age-related diseases or mortality? Or even at this moment in time, can we optimize the function of a person, that person is saying a week later, my quality of life is increased, I have much more endurance, and I'm just feeling better, and I have better social contacts, for example. And that's what I not very often did in my clinical practice, and I always do. What do you want to reach with your body? Because you have it and you have the capacity. Do you want to be optimized to maybe enjoy life much more rigorously? We do that also in clinical practice, maybe at much too late stage. So that's the reason why we are advocating quite successfully here in Singapore to start with optimizing the health of individuals much earlier. And if I say that, we are focusing on aging populations from roughly the age of 25 to 30 onwards at this moment in time. But however, we are also thinking about the next generation. So how can we optimize the health of unborn individuals? And of course, then we should optimize the health of individuals who want to become pregnant. So it's the father and mothers in spe to optimize them. And of course, there is not much evidence around there. But if we would optimize them, they're in good physical, cognitive, social, environmental conditions. Could we therewith already give the unborn child the best opportunities to have a graceful and a very successful aging trajectory? And we already know from studies like the Hunger Winter study that we might be able to change the trajectory of individuals based on the health of the parents. And we absolutely know that of women's health while they are pregnant and smoking, etc., that this is associated with the health of the child. So Therewith, let's not dichotomize it. Let's look at the trajectory of health of every organ system. So why do we start so early? And I really learned from the Dunedin study. The Dunedin study is, for me, it's a beautiful study, very innovative, where they included already individuals at the age of 26, which I would say as a geriatrician, when I've read the first paper, it's very, very young. And what they did in the last decades, they were observationally following these individuals from the age of 26, from the city Dunedin in New Zealand, and they were looking at every health parameter a GP could do. And you see some of the health parameters here on the right-hand side. So everybody can measure the BMI, we can measure lung function, we can measure HDL cholesterol levels, we can measure a CRP. And what you see, they made Z-scores out of it, so they standardized it. And what you see during the aging trajectory of these quite young individuals over nearly 20 years is that it's going from it is better to going worse, which already means that we have in clinical practice something in hand to measure the trajectory of individuals much, much earlier in life than we would do at this moment in time. Of course, I cannot remember that any GP ever asked me, what is your CRP? And can we use that? Maybe not only as a predictive biomarker, but also a responsive biomarker. And I will come to that in a second. But what this observational study really shows, and we are now using that, and lots of researchers using that cohort to build clocks, is that we can detect very easily already changes earlier in life. And these age-related changes are associated, and this is not the causality, but at least we have epidemiological associations with age-related disease onset later in life, because you know that a higher CRP is associated with the onset of diabetes, cardiovascular disease, etc. So, knowing that there is, especially in Singapore, we have an aging population, we have low fertility rates, we have lots of costs, we need the manpower in the country. The government, the universities are really working together with one aim, and this is also my KPI for me personally. What I got from the university is increasing the health span of Singaporeans and of Asians and worldwide, of course, but my judgment is Singapore by 3 years in the next decade. So 3 years in the next decade. So to do that, we have to build an ecosystem. So how do we make sure that the health span, which is the duration without age-related diseases, is going up? We need preclinical research, we need clinical research, we need practice, implementation, and we need the public health physicians, but also researchers on our side. So we have all of them, and we are working very heavily together with lots of investigators, not only from industry, but also from the government, etc. We have many public-private partnerships we are doing, because I think that can accelerate what we are doing in the end. We also have clinics, so we implement it in clinical practice. And we have a nationwide program, which is called Healthier SG, where we capitalize now the cost we are going to spend for each individual on health, and we can spend the money much, much earlier and can therewith invest in prevention. And we also have lovely projects like the Health District in Queenstown, where we dedicate entire districts, including where they live, what kind of environment we expose individuals to a healthy living environment, to really showcase that we can increase the health span of Singaporeans. What do we need, and what is our responsibility at the center? We need to have diagnostics, how to measure the biological age, and we need interventions. How do we treat the biological age? Because I love the idea that I only not diagnose, but I can also ethically and treat individuals into the right direction to lower the biological age, and we already have that in hands. Very often we start with everything we are doing. We are starting as in every specialty with systematic reviews, meta-analysis, but we also, what we recently started to really evaluate the ecosystem, for example, the ecosystem of supplements, producers and the use, etc. And we are starting, and I will showcase you a couple of slides on it. We are testing supplements. What is the quality of it? To really increase the quality of the entire ecosystem, hopefully, in the end. We also recognize that we need educated people. We not only need educated laymen, but we also need peers who can do research and who want to implement preventative strategies into clinical practice. So that's the reason why we started just recently. We founded the Health and Longevity Academy 8 weeks ago. And now we have wonderful programs like executive programs where we focus on executive or multinational companies, etc., to really train them how they could invest into health longevity. We are establishing a master, and we have a summer school, an incubator, which is starting now in 2 weeks' time, which is very exciting. And as Dr. Dodek already mentioned, it's the Health and Longevity Medicine Society, where we bring in healthcare professionals together around the world. We train them. We are writing guidelines at the moment, and we really define the field on health and longevity, because it's a non-defined field at the moment. If somebody is saying somebody is a health and longevity medicine physician, that's not being regulated, and nobody knows really what that is. And we try to regulate that at least a little bit and guide it. Very important in our field is, as already mentioned, we have diagnostics and we have interventions. What kind of diagnostics do we have? We have biological phenotyping, we have clinical phenotyping, and we have digital phenotyping. And I think these are the three emerging things in all specialties at the moment. But for us, because we are a very new specialty, especially the digital phenotyping is very important. What do we do with heart rate variability? What do we do with the number of steps? What do we do with the intake? And how can we measure that with digital tools? But on the other hand side, we have biological phenotyping. Think about the genome, the epigenome, the metabolome, the microbiome, and then you have the microbiome, the gut microbiome, but also the skin and the oral microbiome. So all these are tools we are using in longevity medicine. And of course, we have the clinical phenotyping, and we are really leaning on the success of all other specialties at this moment in time to really get the best measures for heart aging, for the brain aging, for lung aging, and all the organs and the physiological systems in place. On the other hand side, we have interventions, and I will focus on that in the second part of my talk. So we need diagnostics. So before having diagnostics, we need to understand why we age. And I already told you that the chronological age is the greatest risk factor for age-related diseases. So what is driving, not chronological age, it's the time which is ticking, but what is driving the biological mechanisms? And why do we have more wrinkles on the outer side and maybe a lower cardiac function on the inner side? So here you see 9 hallmarks of aging. We now have 12 hallmarks. We are working on another paper with 15 hallmarks. It doesn't matter. But what it shows is the most relevant factors which are associated, or which we know causally already from animal studies, that these are in humans associated, and it's proven causally related in animal studies with the aging process. So you see here cellular senescence, we have genome instability, we have lots of proteostasis, we have epigenetic alterations, which is very important. We have mitochondrial dysfunction, stem cell exhaustion, telomere attrition, and altered intercellular communication. So we understand what's below and what the physiological or the pathophysiological mechanisms are. And we know what is changing during the aging trajectory. And we have plenty of literature in animals, and we are now, since a decade, also translating that to the human processes and making use of big cohort studies and biomaterial. And we also now try to understand how the environment and our habits are influencing these hallmarks of aging. And this is a hugely under-recognized, I would say, field in geroscience, which is more focusing on the biology of aging. But where we live, how many social contacts we have, is really influencing our sleep. That is, again, influencing our metabolic health, for example. So we really have to understand the entire context of not only where our cells are living it, but also we socially, mentally, where we are placing ourselves. So if we understand why we age, we can develop, and we called it 10 years ago, aging footprints. And out of these aging footprints, we making clocks. And what does it mean? And a clock is really focusing on how fast the biological aging processes is, how much accumulation of damage there already is, to then say that somebody is either younger or older. And we just called it, and it's working quite nicely, clocks. So somebody can be chronologically at a certain age, 60 say, and can be biologically 55 or 65. So we are now at the stage where we're really looking at the reproducibility of these kind of clocks, how we can apply them and how accurate they are. Very important, especially in the regulatory system, is that we have to follow the terminology, I would say, being given by regulators. And I already told you a little bit that there is a problem with frailty. Luckily, in 2018, we got ICD-11 codes or 10 codes for sarcopenia, low muscle mass. But now we are working with the concept of intrinsic capacity and vitality capacity in the field. And here I show you a consensus paper we wrote with a couple of members who are advising the WHO on what we mean with vitality capacity. And there we say you have express capacity, which everybody, every GP could already measure. Think about locomotion. Is somebody able to walk, to talk, cognitive, to feel? What is the psychosocial and psychological state of the individuals? And underneath these functions we are expressing in everyday life, we have the higher physiological systems, which are based on biological mechanisms. And here you see lots of these hallmarks of aging, and we call them vitality characteristics. You see them back. So the entire idea is to understand the biology better, to include also social and environmental factors that will lead you to the expression of physiological systems and then the expressed capacities. So we are now working on the vitality capacity, intrinsic capacity, to get good statements in to be able to use them to diagnose how old biologically somebody is. Another movement I really would like to showcase you, because I'm very proud of the executive committee of the Biomarker of Aging Consortium. These young individuals, or younger than me, they really brought of course, with the scientific committee and the founders of this Biomarker of Aging Consortium, they brought and bring us together to talk about what is a biomarker of aging and how can we define how we should validate, for example, biomarkers of aging. So really they're facilitating communication, collaboration, and the sharing of data to, in the end, to have reliable, which is very important, biomarkers of aging, to use as diagnostics, but also to use as responsive biomarkers for the evaluation of interventions. So it's great work which just started 9 months ago, and we already have the first consensus papers now being under revision and nearly in press. So what happened in the past in terms of biomarkers of aging before I show you the definition of biomarkers of aging? Here you see the timeline of what happened in our field, how we use and how we build frameworks of the biomarkers of aging. Everything what is gray is frameworks and guidelines. So of course, most of the times it's based on research, but these were not the groundbreaking ones. In the end, it's just the overarching concept. I would like to focus on the green ones, which are really based on biomarkers, which are based on an omics approach. For example, in 2011, there was the first really hallmark study showing that epigenetic biomarkers can predict chronological age, which is great. And in the end, this is the first generation clock we are using. On the other hand side, in 2012, there was a paper really showing that metabolic bioparameters can predict mortality. And then there was an expansion of all the studies, and there was also validation studies showing us the utility of how good omics approaches are to predict either mortality or the incidence of disease. And especially in the last 5 years, there's an explosion of analysis looking at biomarkers of aging, because now we can utilize all the big biobanks like the UK Biobank, Lifelines, etc., and all the cohorts in the US. So we are really making use of cohort studies which were first dedicated to either predict or predict especially to the incidence of a disease. So some of them are more cardiovascular focused or diabetes focused, and we are now using them to validate our biomarkers of aging. So what is a biomarker of aging? That was our first work. It's a quantitative parameter of an organism that either alone or in a composite predicts biological age, and ideally its changes in response to interventions. So which means that we are not just looking for one biomarker, but a composite, which is very important. It can be a composite of different methylation sites of the genome, for example, but it can also be the combination of a clinical biomarker, say grip strength, together methylation sites of a epigenome genetic analysis, for example. Very important also is that we have 4 different kinds of biomarkers. We have predictive biomarkers, we have responsive ones, and we have surrogate endpoints, which is very important in our field. So you all know what a predictive biomarker is, predicting outcomes. I'm not so much interested in mortality, but especially diseases and incidence of diseases. Very important is to have many more responsive biomarkers. If we do a geroprotective intervention, which means we are using either lifestyle or drugs or supplements to change the biological age, that biomarker is changing. And that biomarker can even be used as a surrogate endpoint. What do I mean? If I show that a certain supplement intervention is lowering the CRP level in the group who is getting the intervention, then I could use that as a surrogate outcome parameter to say, okay, because it's associated in humans with certain health outcomes. Because our trials have one problem, is that our outcomes will deliver in 20 to 30 years time, most of the times if you're including 30 to 40 year individuals, because it takes time until the incidence of a new disease really develops and is measurable. So that's the reason why we really need surrogate outcome markers. Of course, there's lots of discovery also in our field. What kind of type of biomarkers do we have? We have molecular ones, especially the omics approaches are very important. There's lots of investment in the epigenome, but also lipidomics is very important, but also proteomics, metabolomics, and transcriptomics. Physiological parameters, I think, are already absolutely implementable into clinical care, functional performance and physical characteristics. And then we have the digital ones coming from variables. And I think these are very, very important. I would like to show you just one study in terms of biomarkers we detected, and we built clocks just using clinical data. So it's a clinical a biomarker of aging, where we used the UK Biobank with the idea to only include healthy individuals, and the idea, can we make clocks, and hopefully a clock which is an overarching clock, and we called it a body clock, predicting mortality and predicting the incidence of a disease. And that's very important, because if you only have healthy individuals at the age of roughly 50, do we have already markers which are predictive in a clock for the onset of the first disease we would like to prevent? So we took all the clinical data of the UK Biobank, and you see them on the left-hand side. We built on the right-hand side a first-generation clock. So first we calibrated that clock against chronological age, and then secondly against mortality and the incidence of lots of diseases. And then we were actually testing how good these clocks are. And what we said, we were going to establish a body clock, so an overarching clock, but we're also looking at all different organ systems itself and building, for example, a brain clock, a musculoskeletal clock, a renal clock, etc. So here you see first the body clock, and the body clock is calibrated against chronological age. So you see the predicted age versus the real age of 78 physiological measures across 7 organ systems, and only healthy individuals. And what this calibration showed is, it's very nice that the R is just a 0.7 in males and in females. If we would calibrate the clock towards a state that the R coefficient is 1, we would just predict chronological age. And of course, that's not what we want. What we want is spread within that population. So we want a high SD and there was a lower R, that we are not just looking at chronological age. So what you are seeing here, we were quite convinced that that might be a good clock to then took further to predict mortality and the onset of age-related diseases. We took that body clock and we took only, again, the healthy individuals, and we ask ourselves, is that body clock predictive for the onset of all the diseases you see here in this slide? And what you see here, how older or younger individuals are who either develop the diseases within the next 6 years. So it's COPD, cirrhosis, kidney disease, dementia, etc. And what you can see is of healthy individuals at baseline, 6 years later at baseline, the ones who had diabetes 6 years later already were in our body clock 3 years older compared to the ones who did not develop that disease. And of course, we also looked at the accuracy, and it was quite accurate. We also looked at the determinants of not only the body clock being either higher or lower, but also the different clocks. And as the UK Biobank is so rich of data, we really wanted to showcase that it's not only parameters which are physical, but also which are environmental, could influence or be associated, because it's not causality here, are associated with a higher or younger biological age. And what you can see, for example, on the right-hand side, is that even the percentage of green space somebody has around where they are living is associated with a couple of these clocks. I can't go into detail of this wonderful, I would say, analysis and in-depth analysis of so many factors. But what we were able to show is that it's a network, and we cannot just look at biological parameters and at organ function, but we have to take into account habits, the mood, where people live, what kind of noise there is, and take the environment into account. So please refer to this paper to get to study it in more detail. What we also wanted to show is or analyze is, if somebody at baseline is healthy, has a functional decline in one of the organ systems, how likely is it that that person then develops a disease and functional decline in the second tranche of the longitudinal approach to even have a decline in a different organ? So what is the interaction of possible interaction? What is the sequence of decline of different organ system within one individual? And that's depicted here. We did lots of network analysis to see if one organ is declining first, what is the sequence and which organ is declining next. What you see here, we're starting with pulmonary function. If somebody in the first 6 years is declining in the pulmonary function, it's very likely that the following 6 years, that person is declining in cardiac function. If somebody is declining in the cardiac function, it's very likely that the renal function is going to decline. However, there are directions. It's not bidirectional. If somebody declines in the cardiac function, it's very unlikely and not significant that that person per se declines in the pulmonary function. What does it mean? Now we have a sequence of occurrences of decline in organ functions. And if I think with a preventative hat on, we could already not only measure how somebody is doing, but maybe advise to seek help from a different specialty much, much earlier, which means a pulmonologist should refer to a cardiologist, even if the heart is still normal in conventional medicine, but maybe already declining, whereas a cardiologist should refer to a nephrologist, but not per se to a pulmonologist. So this is really the first very small step to see sequences of organ decline. And there was also, I would say, from a management perspective of where I'm coming from the hospital system, is where do we put resources on, and who do we target, and what kind of annual health screens, etc., for what? And I think we have to be much more specific in the end to be cost effective. That organs within our body age differently is already a little bit known. I thought always that the rate of aging within individuals, so not between individuals, but within individuals, is quite the same. However, this is not true. This is a systematic review with lots of meta-analysis of just one example, and that's the example of the aging hallmark, cellular senescence, and the chronological age, and then stratified for different organ systems. What we were able to show here is that the contribution to the aging process within individuals of different organ systems is quite different. So you have much more contribution of cellular senescence as a pathway in the pancreas compared, for example, to the colon or the thymus, or even the vascular system. And if you look at, for example, the brain, you also see that next to the pancreas, senescence plays a huge role. There's much, much more senescence load in individuals who are older compared to a younger population. And the senescence load is much, much bigger compared, for example, to a skin, which means we are now also in the early steps to see not only what a possible biological age of an entire body is, but how different organs within an individual are aging and what kind of mechanisms are behind that. But we know that all of the hallmarks of aging, and this is again just one example of cellular senescence, they are associated with the onset of age-related diseases. And that's also the reason why we really we're able and quite confident with these associations of the hallmarks of aging and the diseases that we would provide now therapeutics to possibly stop this aging process and therewith hopefully prevent these kind of age-related diseases. So here you see the number of studies, the number of markers, of senescence markers being used in different organ systems and in different age-related diseases, where we compared the senescence load in individuals with that disease compared to the ones who do not have that disease. And what you can see, blue is all positive, that individuals with an age-related disease, for example, dementia or COPD, that the senescence load is much, much higher in the organs of these individuals compared to individuals who do not have that disease. And of course, this is just association, it's not causality, but at least hints us into the right direction. Another very important part of the biomarker of aging, as I already said, is methylation. So we now develop epigenetic clocks. So methylation is methylation at GPC sites, and therewith being able, very broadly speaking, to switch on and off genes where the genome is methylated and how often it is, really helped us in just phenotyping it to build the epigenetic clocks. And these epigenetic clocks are predictive not only for chronological age, but it's always good to know, but especially for the diseases and the incidence of diseases and mortality. And it's a presentation on its own to go through all the clocks, but there are so many and they are being validated at this moment in time, lots of cohort studies. And one of the driver of validation and really establishing networks is the Clock Foundation, where they brought all the clocks together and there was give the platform not only for researchers, but also associates to be able to use the material and to bring the field together. So I think this is a great network approach. Biomarkers are not only biological, as I already told you, but especially also now mental biomarkers, really using mental health screening tools, making clocks out of it, are appearing. I'm not sure if they are going to survive, because in the end, we should not have thousands of clocks, but I just want to showcase you that especially industry partners are looking now for clocks which can be used as screening tools, for example, for mental health, which is an important aspect. And there you see the explosion of digital biomarkers and how to measure them. Think about the 24/7 glucose monitoring we are using already in clinical practice from preventative approaches, Think about the measurement of sleep with different devices and the measurement of heart rate variability and etc. in different devices. Companies, but also researchers now bring this immense number of interventions together. I have a conflict of interest here. I'm the CMO, the Chief Medical Officer of New, which is a startup company where we bring in the genome, the microbiome, the epigenome to build digital twins, and therewith build an engine to advise people into certain lifestyle interventions and the use of certain supplements, which is an absolutely evidence-based approach. What does it look like? Such a dashboard. You see my biological age here. I just had dengue at that moment in time. Hopefully now I'm a little bit younger again. But it really shows clients or layman individuals what the possible biological age is and where to focus on and where not. But I think for the entire field, the most important challenge is to make use of all these incredibly amount of data in a sensible way that it's evidence-based and we can do evidence-based approaches. Let's move on to, after the diagnostic part, into the interventions. So where do we stand? And I will talk a little bit, just slightly, about lifestyle, especially physical activity, and then go into the supplements and then into especially repurposed drugs. But each of these ingredients are already a presentation in itself, so please do reach out if you have more questions. And I'm really focusing on what is evidence-based and where do we need more trials, and maybe also in the discussion where is no evidence at all yet and what should we implement in clinical practice around the world and maybe even stop doing. So why intervening? I think that's already now clear. We are aging, we have the incidence of diseases, we understand why we age, we can diagnose it, we have an ICD-11 code we could use, and therewith I think it's important to work towards implementation into clinical practice, and to do so we need evidence-based interventions. One of the evidence-based interventions, I think we can close a little bit the book, is that physical activity is good. We are writing at the moment lots of reviews, so we just did it for the hallmarks of aging, or the pillars of aging, and how we could influence these biological parameters of aging with physical activity. And I can tell you that physical activity, even just a step and taking more step, it doesn't have to be endurance training or a resistance exercise training. We can manipulate the hallmarks of aging, the epigenetic drift, our metabolic dysregulation we can antagonize, etc., etc. So please, I refer to this paper to read about really the mechanisms and how beautiful exercise is in interfering with our aging process. We did, during the pandemic, my PhD students, lots of work to publish lots of systematic reviews to just, I would say, close the book, showing that more steps, more rigorous physical activity is good for individuals. What we did, we took all studies until 2020, and then we updated it in 2021, all observational studies and intervention studies who used a digital device to objectively measure physical activity. And we used the data to then link them to outcome parameters which are relevant for the aging process. So it is mortality, it's activities of daily living, frailty, falls, fear of falling, muscle strength, muscle power, and then cognition. And we wrote separate analysis, separate reviews to see on the left-hand side on these, how strong the association is of the step counts, of the activity counts, of the total physical activity, of low physical activity, sedentary behavior, and vigorous physical activity with these outcome parameters to actually show, okay, is it more the number of steps or is it the number of hours being sedentary, which are associated, once again, no causality, but which are associated with these outcome parameters. And when we then did, in this article, we took all the meta-analysis And then we standardized everything, that we were able to compare it. And then we looked at what is with what physical activity most associated with what outcome parameter, which means if it's a greater circle and the circle is darker, the association, the standardized association is bigger. So what you can see here is that especially the number of steps is associated with the number of frailty, which means is if there are higher number of steps, the likelihood that somebody is frail is much, much lower. And that's the strongest association. If you look on the steps really work in the association of future outcomes. If you look at the sedentary behavior, the associations were not as strong as the physical activity data in itself, so more the active physical activity data, which also means that maybe that we should focus more on every step we are taking than interrupting, for example, the sitting time, etc. I know that's lots of debate and we need intervention studies, but I think this is the first study really showcasing the entirety of the data of objectively measured physical activity and the outcomes. And there's absolutely, we can close the book that physical activity is good for all these outcomes. I am, please excuse, now the slide is not going ahead. Yes, then of course also the intervention. We did lots of randomized controlled trials. Please read the articles where we didn't tell individuals go to the gym, but please integrate physical activity into your daily lifestyle. So we did a little bit and randomized controlled trials in introducing silly walks on the street in Europe to improve physical activity, because we already showed that every step counts. So how can we optimize our metabolic, cognitive, etc. health? And here you see some of the examples how we really nudged individuals into the right direction to enrich their physical activity into daily life activities. And brushing teeth on one leg is the best one and the most done in countries such as the Netherlands. And why do people brush the teeth on one leg? Because you improve your balance in the end. So first we always did diagnostics on the balance, on the strengths, on the endurance, and then we created physical activities which you don't have to do in the gym with very nice positive results. I refer to these papers. Let's go to the supplements and then to the repurposed drugs before closing this session. So you might have heard of the supplement nicotinamide mononucleotide. It's a precursor of NAD, which is a very essential enzyme for metabolism, for every cell activity we have. And as all our organs have cells in there, we would, by targeting NAD, we could have a very pleiotropic effect for all the organ systems in the end in individuals. So what we did in the past 2 years, we did a study on nicotinamide mononucleotide. We included 80 men, 50 years of age, no chronic disease, and we gave NMN in different dosages, 300, 600, 900, and placebo for 60 days. The primary outcome of this study was NAD levels, to really show that by giving NMN, we can measure an increase in NAD levels. And what you can see here is that NAD levels were increasing, and especially in 600 and 900 milligram of NMN. We also, as secondary outcomes, and absolutely this is not a powered study to do so, but we measured, of course, secondary outcome parameters like the 6-minute walking test and the SF36. And what we were able to show is that individuals at 600 and 900 milligram of NMN had a significantly improved 6-minute walking test and a better quality of life score measured by the FS36. These are the first indications. This really needs a phase 3 study, but at least we were able to show that we can manipulate the physiological system and we can increase NAD. Here you see just in a figure dedicated to the change in NAD levels via the dosage, that there's a plateau effect. So 300 gives still an increase in the NAD levels, and it's plateauing at the dosage of 600 and 900. We, because we have the data, we just did a post hoc analysis to see, because we had the positive results on the walking speed and the SF36, we wanted to see if the change in NAD levels during the intervention is associated with, gives the first indication of the change in clinically quite relevant outcome parameters, which is the 6-minute walking test and an SF-36. And what we were able to show, and you see that in the table, is that the NAD level at baseline is not associated with the 6-minute walking test and the SF-36, but the change in NAD level after 30 and 60 days is significantly associated with the 6-minute walking test and the SF-36, which means that each higher increase in NAD while giving the intervention is associated with a better outcome. And that really leads now to a next randomized controlled trial where we are using NAD levels to titrate NMN for individuals to hopefully have a better clinical outcome. Before doing that, we really wanted to invest in, okay, what is the quality of supplements we have? And we all buy all over the counter most of the times. So in here you see just the first analysis of our test or testing the label claim of 2 supplements, and that's NMN and that's urolithin A. What we did is, and we have many more data at this moment in time, we tested the first samples, 10 samples of NMN, and we looked at, okay, what is the claim in the label and is it actually inside the bottle? And what you can see for NMN, but also for urolithin A, that not very often the label claim is correct. So if somebody says there is 300 or 600 milligram of NMN inside, most of the times this amount was much, much less. And even in 2 samples, it was not quantifiable. And the same for urolithin A. And I think this is a huge problem for our ecosystem in terms of quality, that we have to, if we want to include these kind of interventions into clinical care, we first have to make sure that the quality is right. And these are the first results. I would like to also show you a couple of randomized controlled trials we are doing at the moment. Alpha-ketoglutarate. Alpha-ketoglutarate is a very nice molecule with also a pleiotropic effect. What you can see here, it interferes with especially DNA and histone modification, but also reduces oxidative stress, etc. And therewith might interfere with lots of different organ systems, which are depicted here. At the moment, we are running the ABLE study, which is a double-blind randomized controlled trial, giving 1 gram of calcium AKG for 6 months. And the inclusion is individuals who are healthy, 40 to 60, no risk parameters in terms of cardiovascular disease or diabetes. And they have a biological age which is higher using an epigenetic clock compared to the chronological age. And the primary outcome is also DNA methylation in the end, next to lots of secondary outcomes. We also heavily invest into nutritional interventions, and we at this stage really looking at the literature, where to choose and what to choose in terms of interventions for the next randomized controlled trials. We are absolutely dedicated to remove senescent cells, looking at senolytics and xenomorphics. We just finished a systematic review depicted here. I can circulate it if you want, looking at all the ingredients in food we would eat at this moment with xenomorphic and senolytic capacity in animal studies and in humans, and the level of evidence and the proportion of outcomes if you look at the number of senescent cells and the senescence load. And the only thing you have to recognize here that there's a huge potential just by what we eat, what our ingredients are in our diet to possibly influence one of the hallmarks, and that's senescence. We are also really focusing on specific organs within our body, for example, cognition, because there are many more studies, and we are at the moment looking for novel compounds to improve not only the biological age, but also cognition, and also look back into nature, what it serves. And we are heavily looking at GSK3 inhibitors at the moment, and you're already on the right-hand side, see curcumin or sea cucumber or bee pollens from coffee flowers, always potential ingredients who could modulate the GSK3 a pathway, and therewith prevent hopefully Alzheimer's disease and dementia in older age. We also do that for the sirtuin pathway. First, we always look at the pathways. What do we do what kind of ingredients could be available already in food, and then intervene in the end. And you might know that the sirtuin pathway really regulates energy metabolism and mitochondrial function, which is so important, not just for the brain, but for the entire body. The last step before really closing is repurposing drugs. And why do we repurpose drugs? Because they are cheap, they're available, and very important for me as a clinician, I know the side effects of the drugs I normally prescribe. And that's very important from a safety aspect. And I think the prototype of a repurposed drug study is from our dear fellow of Atria, the Academy is near Basilei. He really is the pioneer to bring repurposing drugs into the arena with his TAME study. It's a randomized controlled trial, 6 years, giving metformin to individuals being 65 to 80. And of course, the expected outcome is to have lower cancer risk, cardiovascular disease, etc. What we try in Singapore is really to tackle it a little bit earlier, not at the age of 60, 70, 80, but we are already trying to do that much, much earlier in life. But the TAME study is so important for lots of activities we have in our field. So what do we know about using repurposed drugs? So what kind of evidence is there already? And I can tell you there is a little bit of evidence, but especially in animal models. This was a hallmark study and a landmark study with lots of media attraction, where individuals, very excused, this is 10 gezonde mannen is Dutch. It's 10 healthy individuals aged 60 years of age, and they were exposed 1 year to growth hormone, to testosterone, metformin, zinc, and vitamin D. And what they did, and it's just an observational interventional study, so there was no control, is that the epigenetic age was 2.5 years younger after 1.5 years. So 1 year of intervention and then 6 months younger, 6 months later. So that was really the first study where people thought, okay, we can manipulate the system. However, this is of course such a low evidence study because it's just observational, and we cannot exclude that there are confounding factors. But there are also other drugs we could repurpose. And we just looked at proteostasis modifying drugs, which have the potential to improve cognition. And once again, just cognition, because it's so important for our aging body. On the left-hand side, you see all the drugs which have been repurposed already, and most of the times in animal studies, and which were a couple of years ago in phase 1, 2, and 3, and 4 studies. So there is an exciting field where research really repurpose the drugs to see if we can influence the outcomes. The green color is positive studies and the black ones are negative ones, and the X is studies where they were ongoing at that moment in time in clinicaltrials.gov. Another example is repurposing nutrient-sensing drugs to improve cognition. And what you can see here is on the left-hand side, and you see, for example, GLP-1 agonists, all the therapeutics, and then what kind of species was given, used, and then if it's either for prevention or if it's for cure. And what you see in green is the studies which were significant, had a significant positive improvement on cognition, and the red ones are the negative ones. But what you can see is that there are not many human trials yet. The most number of human trials are in intranasal insulin. And you see in terms of the color coding that there is a trend towards negative outcomes. But that's not bad, because I think our field needs many more negative outcomes, and then hit one which is positive, and then hopefully bring that further into much, much bigger randomized control trials. We are starting to give Rapamycin in a randomized control trial. It's our longer study. Before doing so, we first did a systematic review looking at Rapalox and Rapamycin and the physiological systems and their effect. You see color coding, non-significant. You see in green the positive and partially positive influence of Rapamycin and Rapalox. And what you can see is there are not many studies, first of all. Secondly, that there might be a positive effect on the immune system, and there is not much positive effect on all other physiological systems reported and randomized controlled at this moment in time, despite that many users are already around there. It's estimated that 500,000 individuals already take rapamycin to lower the biological age. I would say with not much evidence. So we do the longer study, a double-blinded randomized controlled trial, 6 milligram per week of rapamycin in 40 to 60-year-old healthy individuals, and the primary outcome is CRP, high sensitivity CRP. So we had the diagnostics, we had the interventions. I just want to close this session really showcasing that it's evolution, but it's also revolution at the moment in the field. There are so many funding opportunities at the moment to do good studies, which we just have to grab. And just here, highlight is evolution, and their slogan, we believe every human has the right to live a longer and healthier life. I think if we can establish that, that would be very great for humanity. We have the Health and Longevity Medicine Academy, Society, where we bring healthcare professionals together. And we have the Health and Longevity Academy, where we have all the incubators, mid-career and master degrees. Please reach out if you want additional information. And we have the government. And I just wanted to showcase MP Henry Quack, who's really helping us. And they are discussing in Parliament that we need much more fundamental research in biology of aging. We need to translate it in humans. And while he was standing there, he was asking, when is the longevity medicine clinic in the publicly funded hospital, Alexandra Hospital, opening? He asked that to the Parliament, and he asked for a response. So at the end of August, we are starting our new longevity clinic in Alexandra Hospital. We now also have collaborations with Sheba and Maier, who is doing the same. So we really want academic partners working together. And we also want to include the private partners. Here you see Chi Longevity to really donate the data to have much more evidence treatments in the end. And this is all what we are doing in implemented in the public health sector in Singapore to eventually be a recognized partner at the World Health Organization, at the FDA, with medical councils, with consumers, insurers, etc., to really change the decade of healthy aging to a more positive, in a more positive way. Thank you so much for your attention. And I love this picture where we really can showcase how beautiful the aging process is.
Andrea, thank you so much for your time this morning for you. That was a fantastic, very comprehensive presentation. And thank you for the work that you're doing. It's remarkable. And we appreciate you being here tonight and you being a fellow on the AHRE Academy. We're honored to have you. Thank you very much.